Hello everyone, I'm Tingshu Chen from CNPC TGRI in China, and I will start my presentation. The topic is the investigation of hydrogen-induced intergranular cracking in cobalt, chromium, nickel, medium entropy alloy fabricated by additive manufacture, specifically the LPBF technique. And the presentation is divided into four parts. First is the background and introduction. For the medium entropy alloy, it's regarded as a material containing three or more principal elements, and it has attracted much attention due to its outstanding mechanical properties. It has relatively high tensile strength and marble ductility compared with stainless steels or other nickel-based alloys. Those people believe it has huge potentiality in both fundamental research and real industry. However, the utilization of medium entropy alloy is not it's limited not only by some academic problems but also some economic reasons because it's too expensive. Especially when preparing some geometrically complex components, there will be a huge wastage in materials. As a result, the additive manufacturing should be a suitable way to use medium entropy alloy because it can simplify the required machining steps, reduce material wastage and save cost. Except the outstanding mechanical performance, the medium entropy alloy also show the reliable hydrogen brittle resistance, even compared with some austenite stainless steels like 304 or 316. It can be attributed to the severely distorted lattice structure due to the coexistence of different elements. This kind of distorted lattice structure can prevent the hydrogen diffuse in the material and thus postpone the occurrence of hydrogen enrichment. However, in our recent research, we found the cobalt, chromium, nickel, medium entropy alloys show different hydrogen enrichment sensitivities. Specifically, for the pre-charged specimen, it shows excellent hydrogen enrichment resistance. However, for the in situ hydrogen charged one, the hydrogen enrichment resistance is significantly degraded. And following the degradation in mechanical properties, the fracture mode also changed to intergranular fracture with almost a clean fracture surface. Except for the influence of hydrogen charging method, the macrostructure also important for hydrogen enrichment because the hydrogen enrichment is the result of the synergetic influence of mechanical, material, and environmental factors. And the macrostructure is the crucial factor of the material. The change in microstructure can definitely modify the hydrogen enrichment phenomenon of the material. As for the additive manufacture of the material, the most distinct structure is the dislocation cellular structures. Thus, a lot of researchers focus on the influence of these typical cellular structures on hydrogen enrichment. For example, Wang et al. They compare the additive manufacture, the pure nickel, with and without cellular structures, and they found after removing these cellular structures by heat treatment, the hydrogen enrichment resistance highly improved. However, except the cellular structures, there are also some other unique substructures. For example, the melting poles, the fusion boundaries, and the columnar grains. These microstructures on different spatial scales can also affect the hydrogen enrichment phenomenon in additive manufactured MEA. However, the investigation of this influence is almost blank. So in this study, we aim to clarify the influence of these microstructural features on different spatial scales on hydrogen enrichment, specifically on hydrogen-induced cracking behaviors. And the pre-alloyed powders containing cobalt, chromium, nickel with equal atomic ratios were used in this study. And we selected the laser powder bed fusion technique, the LPBF technique in this study. The specific parameters is listed in this table. We obtained the tensor spaceman directly from the LPBF machine. And before tensor testing, this spaceman is polished mechanically and electrochemically to remove the scratches and the residual stress on the spaceman surface. And as for the hydrocharging method, the pre-charging method is mainly used to reflect the influence of hydrogen from fabrication processes. However, for the materials used in hydrogen industry, the in situ charging method may be much better because it can reflect the influence of hydrogen from surface environments. Besides, the in situ charging method can also make a hydrogen-rich zone in which the hydrogen-induced damage occurs prefer to nucleate. It is much similar to some real cases that the hydrogen-induced damage preferentially nucleated at the high hydrogen concentration site. Thus, we select the in situ hydrogen charging in this study, and the current density is 0.1 milliampere per square centimeter, and the initial strain rate is 10⁻⁵ per second. Before tensor testing, we first detect the typical hierarchical microstructures. On the middle scale, we can find some multiples or fusion boundaries. And within the pores or within the ligament between two boundaries, we can find some columnar grains with a length ranging from 25 to 65 micrometer. However, the average grain size within the measurement region is about 8 micrometer. It means there should be some refined microstructures to reduce the average value. Thus, we further investigate the microstructures within the fusion boundaries, and we can find some refined grains. Besides, we also find some sub-grain boundaries within the columnar grains. Based on the statistic analysis, we can find the length fraction of the sub-grain boundaries is almost 70%. Then we further detect the microstructure on the nanoscopic scale, and we find the typical dislocation cellular structures with the size of 200 nanometer. And it's also worth noting that no matter in middle scale, macro scale, or nanoscale, we cannot find the annealing twins. It's much different to the conventional manufactured MEA, because in the conventional manufactured MEA, the fraction of anneal twins almost 40%. And for the mechanical properties of the LPBF specimen, for the uncharged specimen, it showed excellent mechanical properties. The UTS almost 800, and the elongation is exceeding 50. However, after introducing hydrogen concurrently, the elongation decreased from 0.5 to 0.15. And following the degradation in mechanical properties, the fracture mode also changed. For the uncharged specimen, it shows typical ductile fracture. Some dimples appeared on the fracture surface. However, after introducing hydrogen concurrently, some brittle features appeared at the edge of the specimen. It corresponding well to the hydrogen-rich zone near the surface, according to the in situ charging method. And further investigate these brittle fracture features, we can find on the fracture surface some multiple features appeared similar to the initial structure. And on a single fracture surface, we can find some periodic patterns. This kind of patterns is much like to appear on the crust cleavage fractures. To further investigate the hydrogen-induced cracking behaviors, we select a subcrack within the fusion boundary regions. And according to the EBS measurement, we can find the crack preferentially propagate along the grain boundary. So it shows intergranular fracture mode. And for the fusion boundary, the first feature is the local grain refinement. This refined grains result in a discontinuous crack morphology. Specifically, these refined grains can temporarily prevent the crack growth and result in the crack deplanting. And then this arrested crack can regrow by crack license. Besides, the crack deflection also occurred due to local grain refinement. And the other feature of the fusion boundary is the local high dislocation densities. This figure show the image of the microstructure before testing, and we can find the relatively high CAM values located along the fusion boundaries. Means the local location densities should be higher than the other part at the fusion boundaries. And this kind of high CAM value distribution still exists even after the tensor test. However, there is a controversial phenomenon that there is a sharp crack, but it is surrounded by high CAM values. In general, this kind of sharp crack, in general, the CAM values around this kind of sharp crack should be low because this kind of crack should be driven by local stress instead of local strain. Although there's a blunt crack tip, for the blunt crack tip, the CAM values should have been relatively high at the crack tip and decrease to the far side. However, in our case, the high CAM values almost constant along the crack path. So this kind of high CAM values shouldn't represent the local plasticity evolution. It should correspond to the initial dislocation densities. And as for the hydrogen-induced cracking along the columnar grain boundaries, without the influence of localized grain refinement, the crack morphology becomes much continuous. However, there's show a wave-like shape region, and around this wave-like crack path, the localized CAM values is relatively high, and we can find an obvious CAM value gap on the different side of the crack path. And for the left grain, based on the Taylor factor map, we can find the Taylor factor is relatively low, which means this grain, the deformation ability of this grain is 3 minutes. Okay, it's high. So the incompatible deformation ability between these two grains should be the driving force for this kind of crack. However, in the crack tip, the crack morphology changed from wave-like to relatively straight. Since there's almost no difference between the deformation ability or the misorientation, so we focus on the substructure, and we can find around the straight crack path, there are lots of subgrain boundaries. And this subgrain boundary, the shape of this subgrain boundaries is well corresponded to the distribution of high CAM values. It means this subgrain boundaries consisted of dislocation structures. It's well known that the dislocations are reversible hydrogen traps, so they can release hydrogen during the tensor test. As a result, these subgrain boundaries can enrich the local hydrogen concentration and then promote the hydrogen-induced intergranular cracking, finally result in a smooth crack region. And after investigated the hydrogen-induced cracking behavior, focus on the deformation mechanisms. For the IPBF built MEA without the influence of hydrogen. In the initial stage of the deformation, we can find some deformation twins appeared. And this figure shows the sample obtained from the ruptured specimen. From the overview image, we can find there are plenty of deformation twins parallel with each other. And within a single deformation twin, we can still find some tiny substructures. According to the high resolution deformation twins. So we can decide the formation of the primary deformation twins. Second, ensure the steady string hardening capacity of the IPBF field spaceman. And after introducing hydrogen, we can find the deformation twins along different tuning boundaries generated at the same time, because the thickness between them are almost the same. And as for the intergranular cracking, we investigate the region beneath the crack path, and we can find the interaction between these substructures and the green boundary. According to the inverse FFT image, we can find these substructures are deformation twins. So the interaction between deformation twins and the green boundaries promote the intergranular cracking formation. And finally, for IPBF built spacemen had excellent mechanical properties. However, when introduced hydrogen concurrently, the spaceman shows relatively high sensitivity to hydrogen burden. And that's all. Thank you very much.